Hello and welcome to this lecture. We are going to talk about two different topics. One for a very quick wind up of this polar decomposition, which I did not mention before. We'll quickly look at that. It's a small and simple consequence of SVD. And then we'll look at some 2 or 3 applications of SVD, how it's used in practice. And it'll also give you a sense of how to think of matrices, how to think of linear maps, how do they show up in real life from nowhere, right? I mean, we already saw in the PageRank algorithm how applications rely on this intuition you build with linear algebra about vectors and matrices and linear maps, and how you sort of look at how do you sort of generate them in real life problems when maybe they don't seem to appear. So there are some nice models and some principles here on how to construct these matrices from in real world and how to associate linear maps with them, how to think of SVD, etc. in that context. So hopefully these applications will give you more of a flavor of how these things work in real life. Okay, so let's go ahead and look at them. So once again, this course is not primarily about applications, it's mostly about the theory and all that, giving you a solid foundation there. But also I think it's good to sometimes see how in the applied world people pick up and connect the dots and use the theory in a very creative, clever fashion. Okay, so let's go ahead and see that. So a quick recap, I'll skip the recap in this lecture. We've been looking at SVD this week, and SVD of a matrix A has this very simple description. A is an M cross N matrix. A can be written as a product of 3 matrices U, D, V star. V star denotes conjugate transpose, so that's U, D, V star. U is an M cross M unitary matrix. Columns are left singular vectors or basically eigenvectors of A star. Okay, A star is a as you know, is a self-adjoint operator, so it would have orthonormal basis of eigenvectors, and those are called the left singular vectors of A. And V is N cross N unitary. V star, like I told you, is the conjugate transpose. Columns of V are right singular vectors, or they're basically the eigenvectors of A star A. A star A again is a self-adjoint operator, and it will have an orthonormal eigenvector basis, and one of those becomes the set of right singular vectors for A, and that makes up the matrix B. And this D diagonal matrix is an M cross N diagonal matrix. Sort of D is like the heart of A, right? So essence of A, and it's got the singular values on the diagonal. Usually you arrange it in decreasing order. Singular values are non-negative, so you put them in decreasing order along the main diagonal of D. Diagonal is basically I and J are the same, right? Row and column indices are the same. That's the main diagonal. And what are singular values? Singular values are square root of the eigenvalues of A star A or A star, right? So of course the numbers differ here, but you can figure out how many you need for an M cross N diagonal matrix. Okay, so that's the thing. So you can see that V star is just a unitary transform. It's not doing much. It's rotating in some way, and D is what is really doing the transform, and it's just a scaling of the coordinates in the basis of the columns of V. And then U is also just a unitary operator, which is again rotating. So you can think of U and V as not doing much, and D is the one that's really representing what A is doing. And so this is a very good way to picture a matrix which could be very big and unwieldy, big large values of M and N, but D has got very few entries, and it gives you a very clear idea of what it is. So this is the power of SVD. It gives you a good feel for how to work with matrices. Okay, so that's SVD. We've seen that before. So there is a connection between SVD and what's called a polar decomposition of an operator. So now supposing you take A to be a square matrix N cross N representing some operator, maybe in the standard basis, right? So then we know A has this U, D, V star SVD again, right? And even if it's an operator, that is true. Now I'll do this little trick of introducing this V star V in the middle, right? So this is U, D, in between U and D we'll introduce this V star V, right? So that's what I've done here. You can see between U and D I've introduced V star V. V star V is I, right? It's not doing anything. But then I'll bracket them differently. I'll bracket the VD V star separately. I'll bracket the UV star separately. So now UV star is unitary. Okay, so you can check this very quickly that UV star will be unitary. If you want, I can check that for you, right? UV star whole star is VU star. So UV star multiplied by UV star, product of two unitary operators unitary matrices is unitary. Okay, so that's something you should be able to easily show. V star V is I, then U star is I, so this becomes I. So UV star is unitary, so it basically represents an isometry. So UV star is an isometry, but then look at what is this, VDV star. VDV star is self-adjoint, right? And since D basically in VDV star, D is like the singular values, which is the eigenvalues of square root T star T. The columns are the columns of V are the eigenvectors of square root T star V. So this is nothing but the operator root T star V. Okay, so VDV star represents root T star V, T star T. Okay, so this is a just reinterpretation of what SVD represents when you have A being an operator n cross n. Okay, so the polar decomposition essentially states this fact. Okay, it says for any operator T from V to V, there exists an isometry S such that T becomes equal to S times square root of T star T. Okay, so why is this called polar decomposition? So this is sort of like it's analogous to, for a complex number, you can always write the complex number as its absolute value multiplied by e power I theta, right? So theta is that argument of z. So this is what this is doing. So the square root of T star T is sort of like the absolute value of T in some sense, because it's a positive square root, right? It's a positive operator. And then S is like a e power I theta, right? It's a rotation, it's like a unitary operator S. So this is always true for operators. So this sort of advances the analogy that we've been talking about between complex numbers and operators in some sense. Okay, so this is polar decomposition. I'm just mentioning it. It's a simple fact from SVD. Okay, all right. So that's all the theory that we want to do in this class. So we've sort of concluded this whole course as far as the theory is concerned. So to really close it out, I want to show you some 2 or 3 applications of SVD. In fact, 3 applications of SVD, maybe, and then show you how people think of how people bring in these linear algebraic notions in practice and use them very effectively. We already saw them with eigenvalue applications, so here we'll see with SVD applications. Okay, so and with that we'll close the course. So this will be sort of the last lecture in that sense. Okay, so the first thing I want to show you is through this collab sheet that I've shared with you through GitHub. So this is sort of shows you how matrices can be approximated. I'm depicting it with images. Okay, so always when you think of a matrix, an image is an easy thing for you to represent, right? So if you have a large matrix, you can represent it as an image, and I've done that here and sort of shown SVD in action. So this is you can think of it as an application in image compression. People use SVD in some image compression sometimes. So this sort of illustrates how that would come about. Okay. So this is a Python 3 Jupyter notebook, a Colab notebook. So you have to import some packages. There is the CV2 package which I'm using. So this is it's an open CV package, open computer vision package. It's a very popular Python package for reading images and all that. All I'm doing is for reading images. Okay. So I took a Gajendra circle picture, IITM GC picture, in low resolution JPEG picture. You can also take bigger images if you want. So this picture is available from the IITM website through the Instagram page that we have. It's one of those pictures, or you can take any other picture also if you want to play around with it. So I put a comma 0 here. I believe the 0 just imports it as a grayscale image. That's what this CV2 IM read does. So basically I'm reading it in grayscale. If you don't read in grayscale, JPEG images have multiple attributes. Some of them have 3 attributes RGB, some of them have a 4th one also. So it can become so it will be it will be a 2-dimensional matrix sort of thing, but each entry will have R value, G value, B value. So red, green, blue value. It can also have other values associated with that. So if you read grayscale, it will read only a matrix. Okay, so that's why I'm reading it in grayscale. So this is just grayscale is just from say 0 to 255 or something like that. Okay, so from white to black, black to white, 0 to 255. So that's the number that it would represent. And this picture actually happens to be a very large resolution picture. I think if I'm not wrong, it's some 3000 by 4000 or some such very big resolution picture. So what I'm doing in the next step is to downsample it. So this is a way to downsample in Python very easily. I can do : : 8. So these when I do : : some 0 and the last row are filled in automatically. 0 and the last column are filled in automatically. So it will just keep the every 8 by 8 value. So I'm just making it a smaller matrix just for convenience. You can have it as a large matrix also if you want. Today's computing algorithms are quite good. They don't mind working with large sizes, but anyway, for us the size is not so important, so we can work with a smaller matrix here. So there is this matplotlib.pyplot package which you can import, and then you can do this imshow command, and you have to use the cmap equals gray. That's important, otherwise it will show you some strange color. So if you do cmap equals gray and plot this, it will show you the image. So hopefully you still remember the Gajendra circle, the two elephants and the familiar picture. You can see it's sort of low resolution and all that, but it's okay. I mean, at least you recognize the picture. So this is my matrix. So this IMG1 is a matrix, okay. So it is some size matrix. It's just got values from 0 to 255 in it, and it can be visualized as a image, okay. So I believe it's got 281 rows and 500 columns, okay. So that's this image, okay. So once I have a matrix, whatever that matrix may be, I can run SVD, okay. So on this image, I run an SVD, okay. So I use the NumPy package for it, which I imported there, np.linalg, linear algebra module. Inside that there is a SVD function, and I run IMG1 on it. So you run any matrix through this, it will give you the U, D and V star, okay. So I am just calling it U, D, V star, and U is the unitary matrix with the left singular eigenvectors, Vs is the unitary matrix with the right singular eigenvectors, and D is the singular values in decreasing order, okay. So it's good to plot D. So remember it will have 281 singular values, right. So that's what it will show you, or maybe 500, but the rest are all zeros, right. So it's not so interesting. So 281 is the non-trivial singular values, and it's good to nicely see them, plot them in log scale and see, okay. For such large matrices, you can see, look at this big drop, right. So there are few eigenvalues which are few singular values, I should be careful, yes, few singular values which are really large, like 10 power 4, 10 power 5, etc. And then there is the sharp drop. It comes down to 10 power 3, well 10 power 3 is still big, but remember the matrix entries are 0 to 255, so you have to have a sense of how big the the norm of every row or column is in the matrix. So it's quite big. So 10 power 3 maybe is not so big, but then definitely 10 power 2 and all is not big, but you can see this big drop. So this is sort of a nice feature. You will see any big matrix you take and find its singular values, it will have this kind of feature. It will usually drop off quite quickly. So this is sort of showing you that it's the matrix, every entry in the matrix is not all that independent. There are some structure there when you see this drop, okay. So that's those are good interpretations to keep, okay. So to bring out that interpretation, I am going to try and approximate this image. How am I approximating this image? So normally when you have SVD, you have the full matrix, U, D, V star, okay. I will only take 10 columns of U and the top 10 singular values from D and the 10 columns, 10 rows of V star, okay. So maybe I should write this down. So we are writing A, U, and then you have D, and then you have V, okay. So this, let's say this is V star, U, D, V star, right. So D will have the singular values on the diagonal like that, okay. This would have the the F1s, F2 along the columns, and this would have the E1 star, E2 star along the rows, right. So E1, E2 are the the right singular eigenvectors, F1, F2 are the left singular eigenvectors, sigma 1, sigma 2 are the singular values, okay. So if you multiply the whole thing together, you will get A. Now what is this approximation doing? I'm only going to take, say, the 10 columns here. I will only take the 10 by 10 here, okay. So this is M, let's say, so I will take M by 10, and then here also I will only take only on this side I will take 10 by N, okay. So this is N. So if you do this, notice the largest sigma values are being accounted for, right. See, A becomes sigma 1 F1 E1 star plus sigma 2 F2 E2 star plus so on, right, all the way till the last one. The last one will be what? Sigma, so you can sort of write this down. So let's say sigma m, fm, em star, right. So it stops there. There are 281. After that, it's just 0 eigenvalues. Let's think about how it will work out. The next ones don't matter. I'm assuming m is smaller than n. Okay. So of all of them together will give you A, and I know sigma 1 is greater than sigma 2 greater than so on. Okay. Okay. So if I want a good approximation, I can stop somewhere here. Okay. So in this product, I will stop somewhere here. Stop at the 10th point. Stop at sigma 10, f10, e10 star. Okay. So that's the same as in this matrix picture, stopping like this. Okay. So when you do that, I get a pretty reasonable, I hope I will get a reasonable approximation for A. Okay. So that's the thinking when people do these kind of approximations. So keep that in mind. Okay. So that's what I've done here. You can see I've taken matrix multiplication. I'm multiplying U only the 10 columns, first 10 columns, D only the 10 by 10, and VS is also I'm keeping only the 10 rows. Okay. So this is a command for that. And then I'm going to plot this IMG APP, which is some approximation. Okay. So you can see here, I took only 10 eigenvalues, there are the singular values, there are 281 of them, I took only 10. So notice here some prime features have already come, right. So maybe there is some confusion here on the top, you can sort of maybe expect that, but at the bottom you see that this pattern got accurately captured, and then there are these the elephants, and you sort of see the fountain. I mean, all of us are maybe familiar with this picture, but still, you can see some important characteristics sort of show up, and maybe there is some sky here. You can sort of see important features show up even with just 10 singular vectors taken into account. Okay. Of course, I can take more. I can take 50, and at 50 you start seeing really the almost a pretty good depiction. If you take 50 singular values, you can see a pretty good depiction of the GC picture. Okay. So this sort of visually shows you how these singular values help in matrix approximation. You have a big matrix, and you sort of expect that there's not so much freedom in the matrix, that every entry was sort of independently generated. Okay, that's at the heart of assuming what a matrix should be, right? So if you assume that every matrix of that every entry in that matrix is sort of independently generated, then you won't get any such great simplification. But you are expecting that there's lots of connection between the entries, and those are captured by this SVD sort of things, with the singular values being very large. So this picture of how the singular values fall is very typical, and it's very important. So this sort of quickly tells you that there is a big drop here, and you can use it for approximation. Okay. So once again, this Colab notebook, you can click on it and open it on Colab. It's shared with you, and this image you can replace with any other image, and I'm not sharing this image. It's there on the IITM webpage in case you want to go see it on the Instagram page. Okay. All right, so that's one illustration / application of SVD that we have seen. Let's see one more. This is from the world of wireless communications, in particular what's called multiple input, multiple output wireless communications, MIMO wireless communications. So in wireless communications, there is a transmitter and a receiver. I'm not going to go into great detail here, but just from a high level, what is the goal? The transmitter will have multiple antennas in which it will send something, and each antenna it will send something. And the receiver will have multiple antennas, and it will receive whatever is being sent as a superposition at the receiver. Okay, so this is a high level. I'll write down what is there in more detail here. So you have transmitter with n antennas, and you have receiver with m antennas. What is transmitted at a particular instance is a vector from the complex vector space. So each entry that this antenna transmits can be complex. You can talk about why it can be complex, etc. Just think of complex as an ordered pair of reals, right? So you can send a complex number, it's okay, it's not wrong. Okay, so you can send complex numbers here on the antennas, and the gain from antenna J on the transmitter to antenna I at the receiver, we will denote as Hij, and this will also be complex. Okay, so this needs some theory here, but I'm skipping all that. Say it's complex. Okay, so the channel is usually written as a matrix, m cross n. Okay, this m and n usually are not very high. I mean, not like thousands, but at least in today's systems they could be 5, 10, things like that. It's not like very small. Today's systems, particularly the 5G systems, may even have very large values of m and n. Okay, so they have some connections with the wavelength of the EM waves being used and all that. So let's not go into great detail there, but this matrix sort of captures what the wireless channel would do from the transmitter to the receiver. Okay. So conveniently you can write what is being received as a Hx plus Z. Okay. So this Hx is basically the map, right? X is getting transformed through the linear map H. H is like a linear map. So look, notice how these linear maps start showing up in a very interesting way. Plus Z, where Z is random noise. Okay. So you can see how these matrices and linear maps sort of show up in some way. Physically what happens at the receiver is that the signals superpose and add, okay, whatever electromagnetic fields that are generated at the antenna, they tend to superpose and add, right. So that's like the theory that we use for modeling it, and so linearity sort of comes in so many different ways, and by the time those signals propagate into your chips and all that, this is a pretty good model for what you want to receive. Okay, so the received Y is Hx plus Z, and Z is random noise. So this noise comes from various electronics at the receiver, and it's unavoidable usually unless you go to really low temperatures. Okay, anyway, so what is the goal when you have Y equals Hx plus Z? Okay, so all that theories, I mean physics is fine, but finally the equation is Y equals Hx plus Z, and you have to recover X plus from Y, right? So that's the goal. So you've been given Y, you have to figure out what X is. Okay, so you can say you want to do an inverse for H, but usually that inverse is done through SVD in a very clever way, because you have to be mindful of Z. Okay, so inverting something is always dangerous when you have random noise, because the noise will get boosted up by that inverse, because inverse multiplies the noise also, right? So you have to be careful about it. So SVD gives you a very nice way of handling all this situation. So how is SVD used in MIMO? So this channel matrix H, you can do UDV star on it, right, the SVD on it, and then you send the V to the transmitter. Okay, so maybe you have some other means of sending it, you send it to the transmitter. So the transmitter, instead of sending X, when it wants to send X, it will send Vx. Okay. Now Vx is okay because it's got the same norm as X. Okay, so you will not be spending more energy than sending X. Okay, so this norm sort of represents the energy of the transmission usually. Okay, so Vx is pretty good. So you can send Vx instead of X, you're not losing much there. So now notice what happens when you send Vx instead of X. Your Y, which is Hx plus Z, okay, the V and V star will cancel and you'll simply get a UD. Okay, so you can see that, right? So Y equals UD V star. You're not getting X now, you're getting Vx, right? Plus Z. So this will cancel and you'll get this. Okay, so that's that. So it's good. So your Y is already a little bit simple. Now at the receiver, you compute U star Y. Okay. So you know U also, so you compute U star Y. Notice what happens. U star Y is just dx plus U star Z. Okay. So notice the only thing that multiplies Z is a unitary operator U star, and that's quite okay because the norm doesn't change. Okay. So the noise doesn't get blown up beyond what it was originally in norm. So that's very nice. Okay. And what you're left with is just dx. What is dx? Dx is just dx, right? So it's a diagonal operator, and you can divide by the singular values in D to estimate X. Okay. So this turns out to be one of the optimal ways of receiving Y equals Hx plus Z, as in finding out X from Y equals Hx plus Z. And this gives tremendous intuition to engineers on how to design systems on the ground and how to build receivers to receive wireless transmissions. Okay. And so much so that this kind of SVD and MIMO play an important role in practical cellular systems. So all your cell phones, even on the communication side, have SVD sitting there, not just on the image processing side like we saw before. Okay, so this is SVD in action in communication. So people who do wireless communication courses probably will meet this at one point or the other. Okay, the last application I want to show you is what are called recommender systems. So all of us use these OTT apps now. Maybe not all of us. A significant fraction of us use these OTT apps like Netflix and Prime Video and all that, and there's always this something called recommended movies. Okay, so maybe you're wondering, how is it that people come up with those recommended movies? What is a strategy for doing that? It's called recommender systems. You can do it in various other systems also. You go to a retail website and buy e-retail website, buy something, it will give you some recommendations based on what you've bought before and based on other things. So all of that sort of depend on these recommender systems and ideas from this. So how does that work? So here is a picture of here is a description of a very loose, simple description, not a very concrete description of how it works. Okay, so let's take the movie user situation, right? So if you take Netflix or any other OTT platform, there are a lot of movies in that platform, and it's got lots of users, right? Maybe lakhs and crores of users, right? And thousands of movies. Okay, now everybody is not going to watch every movie for sure, right? So it's not possible. But you can imagine a matrix A where Aij would be the rating of the movie I by user J. In case user J watches movie I, Aij would be the rating. Okay, so now clearly this is not a complete matrix, as in everybody has not watched every movie and everybody has not rated every movie. So the fact that they watched that movie itself is an indication to me. It shows that, you know, maybe they liked it, whatever, right? So that is at one level. So even at least if they watched it, you know, okay, they are interested vaguely in that movie. But if they give you a rating, then you know for sure that, you know, they really liked it or hated it or whatever. I mean, you know the whole thing about how they like the movie. But even then, everybody is not going to watch every movie, right? So this big matrix is sort of like an incomplete matrix. You don't know many entries. You know only some entries, right? So that's the crux of the matter. Okay, so you should remember that. So notice how in OTT platform where there is no connection to linear algebra, how matrices show up. So you notice that there are these variables. This is variables or entities like users and movies, right? And these are connected. You know, users rate movies, they watch movies, they rate movies. So whenever things are connected, you want to think of these entities as vectors and look at their you know, operations and all that. So you'll see how this works. It's very neat how to think of you know, the linear algebraic settings in places where there is no obvious way to have linear algebra, right? So that this is something interesting. Okay, so you already have a matrix, and what is the goal? The goal, I'll tell you. So the ultimate goal, let me, I mean, you can skip this matrix factorization latent factors for a little while. The goal ultimately is to predict the missing edges. Okay, so forget about, I think I jumped the gun a little bit here, but anyway, predict the missing edges. So this is the goal. Okay, so overall goal in any recommender systems is to predict the missing edges. So let me just go back to the original thing. So I want to predict the missing edges from whatever I know from the matrix A. Okay, so how do I go about doing it? So one very popular method uses something called matrix factorization. Okay, so that's what I'm showing you again, and use something called latent factors. Okay, so you sort of imagine that these movies and users are vectors, right? And sort of think of them as vectors, or think of a vector as representing their characteristics. Okay, so what is the characteristic of a movie? Maybe it has so much violence in it, maybe it has so much, you know, romance in it, maybe it has so much comedy in it. Okay, there's these genres, and you want to put what fraction of the movie goes into genre. Maybe it's positive, negative, right? It's not good comedy, maybe not good romance, not good violence, whatever. So you have positive and negative possibilities, right? So these are these latent factors. And what people try to do from this matrix A, incomplete matrix A, is to come up with a factorization of the matrix. Notice how subtle this is. Okay, so this is where the critical idea comes in. They try to come up with a factorization of this matrix A as Q times P. So what is Q and what is P? Q is an M cross K matrix, P is a K cross N matrix. So this would be like something like this, right? So it would be a Q times a P. Okay, so here are movies, here are users, and this is this K, right? So M, N, and this is K, right? So these K are sort of latent factors. So notice the data has come in, and you don't really have to worry so much about what this K is and all that. Maybe experts would know and they would come up with what fraction this is and all that, but we are just data driven, right? So you just take that data and try and do a factorization here, QP. Put K's, come up with some K columns here, K rows here, and there are multiple ways to do it. There's no unique way to do it, right? So many different ways, and instead of even equals, usually it's only an approximation. Okay, so it's not equal. Okay, you may not be able to exactly get it. So it's only approximation. I've put equal to here. Notice that this is only an approximation. Okay, and you want to associate, sort of think that these K factors are genres, but they need not be, right? So it could be anything else. I don't know what it is, but notice what I'm going to think of. The Q of I comma colon, right? The Q of I comma colon is the column here. So this is Q of I comma colon. Okay, this is sort of MATLAB Python representation for the ith row of Q. So this is the ith movie sort of represented as a vector here, vector over these factors. Okay. And the same thing with the jth user, right? So I'm going to think of this as P of colon comma j, the jth column of P. Okay. And that sort of represents the user, right? It represents the user's liking or disliking of different factors of these latent factors or genres that it may be. Okay, and notice Aij is simply the inner product of Qi colon and P colon j, right? The Aij, ijth entry, the rating or whether the jth user is going to like the ith movie is sort of like this inner product. Okay, so notice how subtle and interestingly things like inner product, matrix factorization, and factors of the factors that make people like movies, not like movies, are entering this picture, and how this problem of building recommender systems for a OTT platform, right, is being expressed in linear algebraic terms. Okay, so this is the nice thing about how when you know the theory and when you understand the theory and how you can relate it to how things in practice work, how these matrices are supposed to look, and then you can use all these things and come up with very nice ideas. So what is the challenge in recommender systems? To find best approximate factorization that can predict the missing Aij's properly. So you get data, so you will have this data, you can generate some, take a partial A, and you would also know the ratings of some movies, keep some as training data, keep some as test data, right, and then try and come up with an algorithm for doing these kind of factorizations. Okay, so very nice application of linear algebra and SVD into, how does SVD come in? I haven't showed you that. So we can see how matrix factorization helps in picturing how recommender systems may be built. Okay. Okay, so how does SVD come in? SVD, maybe current systems, really high-flying systems today, maybe they don't use SVD totally, but SVD is a very good starting point here. Why is that? Because SVD also gives you some sort of an approximate factorization, right? So A equals U dV star, if you write it like that, this can be used to build an approximate factorization, which is what we did in the image also, right? You take only some columns, some rows, and you get a approximate factorization with K being much, much smaller than M or N, okay? So, there are many more ideas today in this recommender systems. SVD is a good starting point for optimizing such factorizations, okay? So, hopefully these three applications gave you a better grounding of how to think of matrices and how to think of these linear algebra and vectors and factorization and inner products and how they show up in various places in totally unobvious ways, okay? So, this is the last lecture, and this is a good place to stop in the course. We've seen quite a few wide-ranging topics, okay, and these have all been summarized in the recap here. So let's just quickly go through that recap, okay. So all these things we saw in theory. We started with vector spaces over a scalar field being real or complex, and then we saw how linear maps are very interesting and how they are represented by matrices, and this fundamental theorem of linear maps which relates the null space and range space dimension, and we used it to solve linear equations, Ax equals b. So that's very powerful. Linear equations show up in so many different places. And then we saw four fundamental subspaces, and then very importantly eigenvalues, eigenvectors. How these one-dimensional invariant subspaces of a linear map really capture what the linear map is. And this helped us in so many applications, right? So particularly eigenvalues, the eigenvectors, they show how linear systems evolve over time, and then even importance of certain graph nodes and all that, page rank and all that. Very interesting algorithms are possible with eigenvalues and eigenvectors. Then we moved on to inner products, norms, orthogonality, orthonormal basis. So this gives you this really projections and inner products are very, very interesting. They measure correlations, they measure so many connections between vectors, and they're very intuitive and very useful. And then we looked at adjoint. Self-adjoint normal operators are very important classes of operators, and general operators are related to them in very nice ways, and this complex real spectral theorem. So it's very important how self-adjoint normal operators have an orthonormal basis of eigenvectors, and they become diagonal in orthonormal basis. Okay, and then we saw positive operators, how they are connected to quadratic forms, maximizing, minimizing quadratic forms. That has a wealth of applications as well, right? Quadratic forms are also very useful to capture some real life behavior. Okay, then we saw isometries, operators which are like rotation. They don't change the relative behavior of vectors. Okay, so and this is very important to know. And finally, the last thing we saw was singular value decomposition, singular values for a general linear map, and how you get this wonderful UD V star, and how that gives you factorization, and how that gives you abilities to use it in so many different applications, approximating a matrix, factoring a matrix, in communications, how to modify your signals that are transmitted and received so that you can easily decode in the presence of noise. Okay, so that's a good recap, and thanks for being along in this course, and hope you have enjoyed it as much as I've enjoyed putting this course together for you, and all the best. Thank you.